Priority queues, heaps, and heapsort. Welcome to this lecture on priority queues, heaps, and heapsort. In this session, we're going to explore one of the most fundamental and highly efficient data structures in computer science, the binary heap, and see how it is used to implement a priority queue and the Heapsort algorithm. These concepts are extremely important because they show how we can manage elements based on their priority in logarithmic time, and how we can sort an array in place with guaranteed optimal performance. We will cover the core concepts of priority queues, the heap structure, and its array mapping, the operations of insertion and deletion, linear time heap construction, and a step-by-step trace of the Heapsort algorithm. Let us begin with the concept of a priority queue. In a standard queue, elements are processed in a first-in, first-out manner. In a priority queue, however, each element is associated with a priority, and elements are retrieved and removed based on this priority. For example, in a max priority queue, the element with the highest priority is served first, while in a min priority queue, the element with the lowest priority is served first. To understand the motivation for heaps, consider alternative implementations. If we use an unsorted array, insertion is fast and takes constant time. But finding and deleting the maximum element requires scanning the entire array, which takes linear time. If we use a sorted array, finding the maximum element is fast and takes constant time, but insertion requires shifting elements, taking linear time. Balanced binary search trees can perform both operations in logarithmic time, but they require significant memory overhead for left and right pointers. A binary heap achieves this same logarithmic performance for both operations without requiring any extra pointers, representing a highly efficient balance. Now, let us define a heap. A heap is a complete binary tree represented sequentially in memory, usually within an array, that satisfies the heap property. A complete binary tree is a tree in which all levels are completely filled, except possibly the last level, which is filled from left to right. In a max heap, the key at any parent node is greater than or equal to the keys of its children. This property ensures that the maximum element is always located at the root of the tree. In a min heap, the key at any parent node is less than or equal to the keys of its children, ensuring that the minimum element is always at the root. Because a heap is a complete binary tree, we can represent it sequentially in a one-indexed array without wasting any space. For any element at index I, its parent is located at index floor of I divided by 2, its left child is at index 2 multiplied by I, and its right child is at index 2 multiplied by I plus 1. This sequential representation eliminates the need for pointers, saving memory, and improving cache locality. Let us explore the core heap operations, starting with insertion. To insert an element into an existing max heap, we first append the new element at the end of the array to maintain the complete binary tree structure. We then compare this new element with its parent. If the new element is larger than its parent, we swap them. This process, known as Up-Heap or Sift-Up, continues recursively upward until the heap property is satisfied, or the element reaches the root. Since the height of a complete binary tree with n elements is at most log base 2 of n, the insertion operation runs in at most logarithmic time. To delete the maximum element from a max heap, we copy the value at the root, which is the maximum. We then replace the root with the last element in the array and decrement the heap size. Because this new root might violate the heap property, we run an adjust procedure, also known as Down-Heap or Sift-Down, to push the element down to its correct position. The adjust procedure compares the parent node with its children, swaps it with the larger of the two children if they are larger than the parent, and repeats the process downward until the heap property is satisfied. The adjust procedure also runs in logarithmic time, ensuring that deletions are highly efficient. When building a heap from an arbitrary unsorted array of size n, there are two primary methods. The first method is repeated insertion, where we start with an empty heap and insert each of the n elements one by one. In the worst case, when elements are inserted in ascending order, each element rises to the root, resulting in a total time complexity of n log n. The second, more efficient method is bottom-up heapification. In this approach, we treat the input array directly as a complete binary tree. Note that all leaf nodes which reside from index floor of n divided by 2 plus 1 to n are already valid heaps. Therefore, we only need to call the adjust procedure starting from the parent of the last leaf at index floor of n divided by 2 and work our way down to index 1. A common question is why this bottom-up heapification runs in linear time rather than n log n. The mathematical proof is elegant. The number of nodes at any given height h in a complete binary tree is at most h raised eel of n divided by 2 raised to the power h plus 1. The time required to run the adjust procedure on a node at height h is proportional to its height. Therefore, the total work is represented by a summation of height h multiplied by n divided by 2 raised to the power h plus 1. If we factor out n, we are left with a summation of h divided by 2 raised to the power h. As height approaches infinity, this infinite series converges to a constant value of 2. Thus, the total work is bounded by n divided by 2 multiplied by 2, which simplifies to linear time complexity. This makes bottom-up heapification an order of magnitude faster than repeated insertion in the worst case. Now let us discuss Heapsort. Heapsort is an in-place sorting algorithm that uses the Max-Heap structure to sort an array. First, we convert the unsorted array into a Max-Heap using bottom-up heapification in linear time. The maximum element is now at index 1. We swap the root with the last element of the heap, reduce the heap size by 1, and call the adjust procedure on the root to restore the heap property. We repeat this process of swapping the maximum element to the end and adjusting the remaining heap until only one element is left. The array is now sorted in non-decreasing order. Let us trace heap sort with a numerical example. Suppose we have the unsorted array 12, 11, 13, 5, 6, and 7 with a size of 6. We first perform heapification. The leaves are 5, 6, and 7 at indices 4, 5, and 6. We adjust starting from index 3, which is 13, 5. Since 13 is greater than its child 7, no swap occurs. We then adjust index 2, which is 11. Since 11 is greater than its children 5 and 6, no swap occurs. Finally, we adjust index 1, which is 12. Its children are 11 and 13. The larger child is 13 at index 3. Since 12 is less than 13, we swap them. Now, 13 is at the root and 12 is at index 3. Since 12 is greater than its child 7, the heapification is complete, resulting in the max heap array 13, 11, 12, 5, 6, and 7. Next, the sorting phase begins. In the first iteration, we swap the root 13 with the last element 7. The array becomes 7, 11, 12, 5, 6, and 13, and we adjust the remaining 5 elements. The children of the root 7 are 11 and 12, so we swap 7 with the larger child 12. The array becomes 12, 11, 7, 5, 6, and 13. In the second iteration, we swap the root 12 with the last element of the heap, which is 6. The array becomes 6, 11, 7, 5, 12, and 13. And we adjust the remaining 4 elements. We swap 6 with its larger child 11, and the array becomes 11, 6, 7, 5, 12, and 13. In the third iteration, we swap 11 with 5. The array becomes 5, 6, 7, 11, 12, and 13. We adjust the root 5 by swapping it with its larger child 7, resulting in 7, 6, 5, 11, 12, and 13. In the fourth iteration, we swap 7 with 5. giving 5, 6, 7, 11, 12, and 13. We adjust the root 5 by swapping it with 6, resulting in 6, 5, 7, 11, 12, and 13. To summarize this lecture, we studied priority queues and saw how binary heaps provide an efficient implementation. We defined max-heaps and min-heaps and explained how complete binary trees are represented using arrays. We detailed the operations of insertion and deletion and proved mathematically that bottom-up heapification builds a heap in linear time. Finally, we traced the Heapsort algorithm, demonstrating how it sorts an array in place in guaranteed n log n time. Heapsort is highly valued because of this optimal worst-case performance and its minimal space requirements, making it a cornerstone of algorithmic design. Thank you for listening, and in the next lecture, we will continue exploring more advanced topics in algorithms design and analysis.